So just as a quick reminder, we were thinking about genetic drift going forward in time, and we were thinking about how the probability of two alleles being identical changes, and we worked through this recursion, the logic of it, right? That there's chance 1 over 2n, two alleles came from the same parental source in the immediately preceding generation. That's one way they could be identical, or that they didn't come from the same parental source in the immediately preceding generation, and that they were also identical by that previous time point. So we worked through that. I show in the notes how that is equivalent to writing it in this form. Okay. So remember the core of this is this chance that you come from the same parental source in the immediately preceding generation. Okay. Right. So the very last thing that I talked about yesterday was this concept of the effective population size, and I tried to give you a qualitative feel of what that concept meant, and I want to briefly go through 3 very common ways that real populations differ from that mathematically ideal population, and ways we can then calculate the effective population size. So the first of those is fluctuations in changes in population size, right? So the ideal population assumes that the population size is constant. So what about if the population is changing in size? Well, it turns out a good way to think about that is to then think about what is the chance that two alleles would not be identical. Well, for two alleles to not be identical, that would just be using this result. So this is the constant population size case, the ideal population size case. That would be 1 minus 1 over 2n to the t. And I just want to use an approximation here. If 1 over 2n is small, so this is 1 minus something small, we can use this relationship here that 1 plus x, if x is in absolute value, is small, is approximately e to the x. So this is the first order Taylor series approximation of that. So this is, we'll just say that e to the minus 1 over 2 n to the t. Okay, so that's our constant population size case for two alleles to not be identical. What if the population size was changing each generation? Well, one way to think about it is for the two alleles to not be identical now, it means that they didn't come from the same parental source in the previous generation. So that's constant n, and now we'll do the changing n. So they couldn't have come from the same parental source in the immediately preceding generation. And we also needed that they didn't come from the same parental source in the generation before that. All the way back to the beginning, right? Does that make sense? Okay. So what we're going to try and ask now is, this real population that's changing in size is equivalent to an ideal population of what size to experience the same rate of inbreeding, okay, of becoming identical. So in other words, we need this thing to equal this. And that would be the effective population size. Well, the way we do this is we can think of this one as e to the minus 2n, or sorry, minus 1 over 2n t minus 1. This is e to the 1 minus 2n t minus 2, etc. Okay? And so what this, you'll hopefully remember that if you're multiplying these things with a common base, you can just add up all the exponents. So we get 1 minus 2n t minus 1 plus 1 minus 1 over 2n t minus 2 plus 1 minus 2n naught. Okay? So that, and there will be t of these terms, right? Representing the t generations. So what we're saying is this thing should equal this thing. So we want to find, so really what we're saying is this bit has to equal that bit. Right? So, so we can do that, and what we find is all the 2's cancel out, and we get 1 over 2ne is equal to 1 over t plus this summation of t going to, or how do I do this? J going from 0 to j going to t minus 1 over n j. Okay. What this, or you can flip this, just take the reciprocal of that, and you have your effective population size. And what that means is the effective population size is equal to the harmonic mean of the actual population sizes. Okay? So the harmonic mean is the reciprocal of the average of the reciprocals. So here you're adding up all the reciprocals, dividing it by the number of them. So that's just your regular arithmetic average of the reciprocals. And then to get the NE, you would take the reciprocal of that. So that's the harmonic mean. The thing about harmonic means is small values have a large effect on determining a harmonic mean. And so the example I often give is if you had a population size that was changing from 100 to 1,000 to 10,000 to 100,000 to 1,000,000, the harmonic mean of that is about 450. The arithmetic mean is over 200,000, right? But these generations of small population size have a large effect on determining what the effective population size is. So again, here the logic is, what we're doing is we're taking a particular aspect of genetic drift. Here we're looking at genetic drift through the lens of inbreeding, of becoming of a probability of alleles being identical. And we're using that as the way to set what would happen in a real population and try to make it equivalent to what would happen in the ideal population, and in that way calculate, we're saying that the amount of genetic drift as it affects this rate of inbreeding, this probability of being identical. This is you need this effective population, or this population size in an ideal population for it to behave in the equivalent way. Okay? Question? Pardon me? I don't think so. Because you're taking, so what you're doing is essentially taking the average of these reciprocals. Yeah. 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 Well, I mean, so T here is representing the number of generations, so it's dimensionless. Okay, so that's the first example of how one can calculate effective population size with some violation from the ideal population. The next one that I want to talk about is thinking about species that have two separate sexes. You have males and females, and you need to reproduce by combining a gamete from a male and from a female, which is not what we assumed in the ideal population, right? In the ideal population, we pick gametes completely at random to form the next generation. So let's think about how that matters. And the way we can do it is, again, thinking about, in this equation, the whole thing that drives it is the chance that two alleles will be identical from the immediately preceding generation. So I think of that chance as calling it the probability that two alleles will be very recently identical by descent. That's the way I think about it anyway. So in the ideal population, that's just 1/2n. So let's think about the equivalent thing if we have these two sexes. So now if I pick two alleles completely, if I pick two alleles at random, I sample two alleles at random from the current generation, what do I need to happen for those alleles to be identical? Well, here's one thing I need to happen. So I need yeah, thanks for telling me that. Is that okay? You can also follow along in the notes. Everything I have is also in the notes. So one of the things that we need to happen, or one way that two alleles could be identical from the preceding generation, is that they both came from a female in the immediately preceding generation. So let's think about what is the chance that both alleles came from a female in the immediately preceding generation. Well, let's think, first of all, what's the chance that any one allele came from a female? Any female. We're not talking about a specific female, just any female. What's the chance that if I grab and just sample one allele, the chance that it came from a female? It's a half, right? So what the chance that, so I need both of them to come from a female. So the chance the first one is from a female, and, magic word, ding, 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 a chance that the second one comes from a female is also half, so half times a half is a quarter, right? So, no, we're sampling alleles at random from the population, not from the same individual. So we get a quarter. So that's the chance that they both come from a female. Both. Then those two alleles won't be identical just because they came from a female, right? We need them to come from the same female, right? So, okay. So then, so the way to think about that is the first one came from some specific female, right? We've already said they're both from females. We've accounted for that. The first one comes from a female. It's the chance that the second one comes from the same female. Well, that will just depend on the number of females. The number of females at that previous generation, yeah? So now we have two alleles that we sampled from the current generation. We know they both came from the same female. Are they the same allele? They might not be, right? Because that female has what? She has two, right? So we need the chance also that that second allele came from the exact same allele as the first one came. And that happens with a chance half, right? So I'll put in an extra half here, okay? Or maybe I'll leave it out so we can. So this is chance, or same female, given that they're both from females, and then this is that they're the same allele from within that female, right? Okay. So that is one way that two alleles that I sample at random from the current generation could be identical. Is that the only way? Right, we need, so what word do I need before you say male? They could be identical this way. Pardon me? Or, right? That's our magic word. Magic word, and if they both came from the same female, could they have both come from the same male? No. So those are what? Mutually exclusive possibilities. We can use our OR rule. We can just add them together, and everything would be exactly equivalent, right? We get the 1/4. The only thing we're changing is now it depends on the number of males. At t-1. I'm just putting the t-1 to remind us that this is from the generation back. Okay? And the half. Remember, it's this probability of being identical from the immediately preceding generation that drives everything in the ideal population. So in other words, what I'm saying is, this thing, if we want to figure out what would be the equivalent amount of the way drift would affect things equivalently in the ideal population, this thing has to be equal to this thing. Okay? So we just do, you know, the basic algebra you learned when you were 12 or whatever, 10 or whenever it is you learn it. That part's straightforward, and so I'll just write it out, and you get 4 and F. I'm going to drop the t-1s so it's less messy. So we get this, which I'm just going to write it in another form. So we can write it like this, or we can write it like this, of 4 times alpha times 1 minus alpha times the total population size, where alpha is just the fraction of the population that is male. Okay, in other words, so this is the sex ratio. Okay. So think about what this means. So alpha is always, of course, has to be between 0 and 1. If alpha is a half, our standard sex ratio, what happens? We get a half times a half is a quarter. That cancels with this 4, and we just recover our basic result. Okay? So we should feel good about that. This seems sensible. But if the sex ratio is anything other than a half, then this value, or let me make it easier, this value will be less than 1. So any biased sex ratio, male biased or female biased, is going to make the effective population size less than the actual population size. Last one I want to do is slightly more tricky, but in some senses, the most important of them. It turns out that there's kind of a hidden assumption that about the amount of variance in reproductive success in the ideal population. And we'll see that in this next example where we are more explicit about alleles being identical. So we're not going to think about separate sexes in this case. Next case that I'm going to do, you can do a more detailed version that also incorporates separate sexes, which is interesting for other reasons, but I'm not going to do it today. What we are going to do is we're going to make the assumption that you can't reproduce by self-fertilization. Okay, we will make that assumption, although it kind of makes a trivial difference, but it allows the math to work out in a nicer way. Okay, so we're going to assume in the previous generation there's nt minus 1 individuals, and they're going to produce nt offspring. And I'm going to use ki to represent the number of offspring produced by individual I in the parental generation. Okay? So the way we're going to get to figuring out that probability of being recently identical by descent is by figuring out the probability that 2 alleles came from the same came from parent I, and then we'll sum across all the possible parents. Okay. So what is the probability that 2 alleles came from the ith parent? Okay, so in the notes I've used SI to represent that. So we're working on the probability that 2 alleles both came from the ith parent. Okay, so first we need, we've said there's no selfing allowed. So for 2 alleles right now, in the current generation, when I sample them, to come from the same parent, that means I have to have sampled alleles from 2 different offspring, right? That's the only way. So what's the chance? So the first allele comes from any offspring. So first thing we have to think about is what's the chance that the second allele we sampled came from a different offspring? Well, that's just the chance that we sample any of the other offspring in the current generation. Right? So if you think about this thing will basically be 1. But this is where I said we include this assumption of no selfing. It will make the math work out more elegantly, but it doesn't really matter if you make that assumption because this thing's basically 1 anyway. Okay, so we need this. All this is saying is we've sampled 2 alleles in the current generation from different offspring, but what we're trying to figure out is the chance that they came from the same parent. So then we need to know what's the chance that the first allele that we sampled came from parent I, right? Because we're really trying to figure out the chance they both came from the ith parent. Okay. Well, the ith parent produced ki offspring, right? So amongst all the n offspring right now, the chance that the first one the first allele I grabbed came from one of the ith parent is just ki over 2ni, or not I, 2nt. Okay, right? There's 2n alleles right now. Ki of them came from the ith parent. What's the chance that the second one came from that same parent? Pardon me? Sorry, I guess I couldn't quite hear you. Ki minus 1, yes, right? We've already accounted for 1, so there's only ki minus 1 left out of the 2, minus 2 actually, right? Because we know we've already accounted for the fact that the first one came from a different individual in the current generation from the second one. So when we think about the second one, there's already 2 alleles removed. There's the actual one plus the other allele that was in that same offspring. Okay. So you could rewrite this as 2 times n minus 1. Okay? So I just rewrote that as 2 times n minus 1. Yeah?
So ki is the number of offspring?
Yes.
And then each offspring has 2 alleles?
That's right.
So should it be 2 ki?
No. So if you think about it, right, because you don't want to double count, right? Actually, this will come up later. Well, I'll leave it for a second. Yeah, so you don't want to, essentially you would be double counting if you do that. Right, so I have 2 offspring. In real life, I have 2 offspring. And my wife has 2 offspring. They are the same offspring, actually. But we don't, right? You don't want to double count. You see how the double counting can occur? Okay. Okay, so you'll notice this n minus 1 nicely cancels with this. N minus 1, that's where we... This is the chance that the second allele that I sample comes from a separate offspring, right? Because I'm sampling 2 alleles at random from the population, and I'm requiring that they need to come, in order for them to come from the same parent, when I've assumed no selfing, they have to come from separate parents. Okay. So this becomes ki times ki minus 1 over 4 n t squared. Yeah? Okay. So that's just the probability that 2 alleles came from the same parent, not just the same parent, they came specifically from parent I. And so when I think about the probability that 2 alleles are recently identical by descent, I would have to sum up from I equals 1 across all the possible parents, Si, and I have to include a factor of 1/2, because the Si as I've defined it is just the chance that 2 alleles came from the same parent. We also need the chance that they're the same allele from that parent. So that gives us an extra factor of 1/2, right? Okay. So we have 1/2. I'm going to pull out the 1/2. 1/2. K minus 1 over 4n. And okay, this is where it's useful to note that the number of alleles, this is the number of alleles in the current generation, has to be equal to the number of parents in the previous generation times the average number of kids that they have. Right? So, yeah, okay. So let's just expand this part out. Is there a question? Yes, thank you. I just want to make sure I'm not skipping a step that I wanted to show. Okay, so we expand this out, and we get 1/2. Or actually, I'm going to pull this whole thing out, so we get 1 over 8 n squared times this summation. If you multiply this, you get a k squared term minus the sums of all the k's. Okay, you with me? And I want to make one substitution. So where have I lost my k bar somewhere? Okay, so let's expand this. When we expand this out, if you all right, this is so k bar. Or I'm going to leave that for now. This is the sum of the squares, right? And I'm actually going to put one factor of n in here and one factor of n in here. Okay. So let's look at these two terms. This one is easier for people to look at first. What is this thing? There are different answers. What is just that part? It's the average, right? So there we get a k-bar. This is adding up all the squares, dividing by n. So what that is, any idea what that is? That's the average of the squares, right? Or it's the expected value of the squares. Have I ever written anything like that before in any context? Variance, right? As soon as you see that thing, that reminds you of the variance. Right? There's that, which relates to the variance. So, in fact, if you just rearrange that, you get what? You get it's equal to the variance plus the square of the mean. Okay? So now, what do we have? We have 1 over 8n. This thing, which is equal to the variance of k plus k bar squared. Yeah? So we have the variance of k plus k bar squared minus k bar. Okay. So remember, this is the mean number of offspring produced. This is the variance in the number of offspring produced. The variance, so this is a variance in reproductive success. And that's our probability of being identical by descent, which in it means it has to be equal by definition to 1 over 2ne. So at this point, it's just simple rearrangement to solve for the effective population size. Whoops. K bar squared. Okay, so it works out to this. Now let's think about, let's assume that the population size is staying constant. If you go through in the notes, I was quite careful about keeping track of whether we're talking about n at time t or n at time t minus 1. I stopped doing that somewhere along the way, but you can go back to the notes and follow it through. But it ends up not being 4 because I've put in I've accounted for this relationship. Well, this is actually I've already accounted for that 4 in there. So if you follow through the notes, I don't want to go back and trace where exactly that comes through. But what I do want to point out is, so remember, if the population size is staying constant, that means k bar has to equal 2. So k bar squared has to be 4, right? So then this becomes 4n over the variance in K plus 4 minus 2. Yeah? So, or I'll just leave this as plus 2. Okay? So when will, for any to be equal to n, what do we need the variance to be? We need it to be 2, right? So if the variance is 2, then we get 2 plus 2 in the denominator. That cancels with the 4, and we're left with n. So the implicit assumption of the ideal population size, of the ideal population, is that the variance is 2, and that the mean is 2, right? Which is a property of the Poisson distribution, that the mean and the variance are the same. That actually comes from in this ideal sort of Fisher-Wright population of constant size, at least at large n, that the reproductive success of any individual is just, it's Poisson distributed with mean and variance of 2. Okay. Well, it turns out pretty much every time that anyone has ever measured reproductive success in a real organism, it's not 2. It's almost always bigger than 2, often way bigger than 2. There's a ton of individuals who produce 0 offspring, and a bunch of and some individuals that produce more, sometimes a lot more. When that variance is greater than 2, right, that means this denominator will be greater than 4, and the effective population size will be smaller than the actual population size. It's quite interesting to work this out with separate sexes, because you can see then how the variance in reproductive success of males contributes, and the variance of reproductive success of female also contribute to this. And as you might know, in many systems with sort of strong classic sexual selection, the variance in reproductive success of males can be massive. Okay. Okay. Yeah. Yeah.
Reproduction. So, which of the assumption which you are assuming here doesn't hold in reality?
All of them. Yeah. So, yeah, I mean, I'm pretty sure I could say with 100% confidence there's no real population that stays exactly constant in size. In fact, many populations that people have done the hard ecological work of monitoring their dynamics, they change in population size often quite a lot. Oh, no, sorry, that doesn't matter. I thought you were asking which of the 3 things we've discussed this morning. For example, the event should be independent. Yeah, I'm not sure I quite understand the question. I mean, what going through this exercise shows is the thing that matters is the variance in reproductive success. And this is trying to what I was mentioning in the beginning of yesterday's lecture. Here's a case where we started thinking about the chance that 2 alleles came from the same parent, and we worked through this in what I feel like was sort of a very natural way, and boom, out comes the variance, kind of unexpectedly. And this is what I was mentioning yesterday, that the variance rears its head all the time in evolutionary biology. So it's important to really know what it is formally, and then you can recognize it when it starts popping up. Okay. Oh, that's a good, wait. Okay, let me stop you for 1 second, because that's an interesting point. What if there is no variance in reproductive success? Then how does the actual population size compare to the effective population size? Yeah, you can double the effective population size. That is what conservation biologists do. If you're trying to conserve a species, and you might be worried about the loss of genetic variation, right? So you essentially are worried about drift. You want to try and slow down drift. So the best thing you can do would be to increase the population size. Well, that would be nice. If you're doing something like keeping a captive breeding program, you can't increase the population size because you have limited space capacity. But what you can do is you might be able to reduce the variance in reproductive success, right? Try and get everybody to contribute as equally as possible to the next generation. Okay? You'll notice that even if I reduce this to 0, you're still experiencing genetic drift. It's not that the effective population size becomes infinite, and the reason for that is essentially because even though you're saying in that case you would require exactly 2 offspring from every individual, but there's still the sampling that occurs within an individual, right? You might get the same allele out of one parent twice. Sorry, I cut you off in the middle of your question because I got excited about that other point.
So I'm just saying that, so imagine scenarios, actually the theoretical reproductive fitness is actually identical, but still you could give, birth to the next generation in a Poissonian fashion.
Yeah.
In that case, right, so VK would
equal 2.
Equal to 2,
yeah.
Exactly, and then you would get N equals N.
Yes.
Like, my interpretation?
That's right. That's right.
So that is, I don't know
so remember, of course, when we were playing the genetic drift game, right? Some diploid individuals contributed more to the next generation than other diploid individuals. There was variance, but it turns out that would be like a Poisson type of variance. Okay. I guess my main point there was that variance in reproductive success in real populations is often much greater than that, and that again leads to that the effective population size will be lower than the actual population size. So in reality, actually, all of the 3 things that we talked about, so we talked about changes in population size, and one, if in a naive way, you might have just taken the arithmetic average, but it turned out the thing that mattered was the harmonic mean, which is typically much lower than the arithmetic mean. We talked about separate sexes, and whenever you have a biased sex ratio, biased either way, you get a reduction in effective population size. And we talked about high variance in reproductive success. Again, that reduces the effective population size. And so the thing I want you to think about is, why is it that all these things cause a reduction in the effective population size? Or really, the better way to think about it, why is it they cause a sort of an increase in the amount of drift compared to the ideal case? So just pause and think about that for 10 seconds. What's the similarity between all of those things conceptually? The way I like to think about it is, in all 3 of those cases, what you're doing is you're forcing a large number of alleles at some point to come from a small number of individuals, right? So when the population is changing in size, whenever that population size gets low, all of the alleles have to come from that small set. Right? When you have a biased sex ratio, in some species you might have a small number, or someone was telling me at some point in India in the last, I guess, 30 or 40 years ago, that for elephants, because the males had been hunted so extensively, the sex ratio was badly biased, right? There was a small number of males compared to the females. Well, remember, it doesn't matter that there's a small number of males. Half the genes have to come from that small number of males. So you're forcing your sampling for half of the genes in one generation to come from a small subset of the individuals in that generation. And the variance and reproductive success model that we did at the end is really sort of almost conceptually identical to that, right? The high variance and reproductive success means some parents have contributed a ton to the next generation and others not at all. So what that means is that in the current generation, a lot of those alleles are being forced to being sampled from that small set of parents, right? So you get these strong drift events, right? Whatever allele happens to be lucky enough to be in that rare male elephant, not by any virtue of what that allele does, it gets overrepresented in the next generation. Whatever allele for an individual that has high reproductive success, it just happens to be in that individual, gets overrepresented. Okay. So I hope you have some feel for what effective population size is. Again, I don't particularly like the term because it puts everything on this idea of a population size. And really what I want you to think about that is as a metric of the strength of drift. Right? It's not really about the number of individuals there. Okay, so we've been thinking about, well, okay, so here's an example of the genetic drift game, and I've drawn some arrows connecting the lines of descent. Here's another a figure of a genetic drift version of the genetic drift. Yeah. Yep. Yes. I don't think I'm following what you mean by fluctuation.
I think he means how do you introduce, so he thinks that genetic drift is introducing variation back into the population. So then
right, okay, so right now we're not thinking about any mutation, right? So we're, one way to think about it is the variation, like when we played the genetic drift game, the variation is there in the beginning, and we're just, there's no new mutation added. So we're just thinking about that loss of variation, okay? Certainly what genetic drift does causes fluctuations in allele frequency, right? So in this example, what I've called the B allele of the A locus, the B allele has fluctuated increase in frequency, but that doesn't mean that it might not go down in frequency if I continue to play this game forward. So there are those kinds of fluctuations. We're going to think very explicitly about mutation in a second. Okay, so, but I want to think not at all about mutation for now. So here's a version of the genetic drift game played on its side rather than vertically, going from the past to the future. I really like this figure. This is from a figure from a nice sort of primer textbook on molecular population genetics by my colleague Asher Cutter. So here's the game played forward in time. But what we're going to start doing now is thinking about genetic drift from a backwards perspective, going backwards in time. And it turns out this is an incredibly powerful and useful way to think about genetic drift that is really the basis for much of modern molecular population genetics. Okay, so what this figure shows is the genetic drift game played for some long time. Here we are in the present. We can trace all of these lineages back, the current day lineages, to when they come together or coalesce at a common ancestor. And that's what's so here, this figure represents sort of all, it's meant to represent all the individuals in the populations, and the ones in the dark purple are the ones that you might actually have sampled in your genetic sample. And so this is just taking this figure and straightening it out, and you get this genealogy, okay? So this is the genealogical history of this sample. And I want to emphasize that to begin with, it's really useful to think about genealogies without any mutation, right? So there could be mutations that have occurred along this time span, but ignore that for now. Regardless of whether that has occurred or not, this is the true genealogical history of this sample, which we know because we played the game, right, to create this sample. So that's true for any sample of genes. It has some true genealogical history. Okay. So this is just a close-up of that. Right, so again, as we trace any two alleles back, say this one and this one, they will come together at some point. These two come together here. These two there come together in the much more recent past. If I think about this one at the bottom and this one at the top, they don't come together until way back here, right? Coming together or coalescing is the term we use. So so what we're going to think about is if we sample two alleles, how long does it take? If we sample two alleles at random, how long would it take for those alleles to coalesce? Well, kind of the point of the last figure is it would depend on which two alleles you were talking about, right? Some of those alleles coalesce in the recent past, some of them coalesce in the distant past. So there's a distribution of coalescence times for any two alleles. And what we're going to work out is the probability that two alleles coalesce 10 generations back or 100 generations back or 100,000 generations back. Okay. Right. Before I do that, I'm just going to show you one more thing, and then I'm going to ask you to forget about it for a second. So I emphasize that this is the genealogy. If there was no mutations, all of these samples would be identical to each other, right? If a mutation occurs somewhere along here, let's say a mutation occurred here, that mutation would be shared by all of these samples and not in common with any of those, right? And similarly, if a mutation occurred here, it would be shared by just these two samples and not by any of the others, right? So here's a figure that illustrates that. So here's a genealogy, and mutations are drawn on it. So here, so you're imagining some stretch of DNA. Here's a stretch of DNA with all these sites. You imagine this green mutation happened to occur at this site. It would be shared by all of these samples. And as opposed to this mutation here that occurs along what we call a terminal branch, and so it will only appear in one of your samples. Okay? And so this is the way people often look at real sequence data, and they sort of summarize it by what we call a site frequency spectrum. So this is these are what we call the singletons. So this is the number of sites at which there is a variant that occurs in only one sample. So that one I was just showing you, this thing here represents a singleton. According to this figure, that in this collective sample, there are, whatever that is, eight mutations that appear in only a single sample. There's 4 mutations that appear in 2 samples. There's 2 mutations that occur in 4 samples. I think those, or 6 samples. Those are these 2 that would occur then in all 6 of those. Okay, so that's sort of the real way one can think about sequence data. So the mutations Of course, in reality, we don't actually get to see these genealogies. We see the mutations, and we can use them to make an inference about the genealogical history. But regardless of whether those mutations have occurred or not, there is a genealogical history. And that's what I want to focus on first. That's really what the coalescence is based on. Okay, the mutations, in some sense, the mutations are the thing we're empirically interested in. We look at a sample of DNA and we're trying to understand the variation in it. But really, the way we can understand that is as a reflection of the genealogical history. And so our focus for now is going to be just on the genealogical history. Then we'll kind of throw on the mutations almost as an afterthought. Okay? Okay. Right. Okay, so so we want to think about the probability that two alleles will coalesce some number of generations in the past. And for many of you, certainly it would have been for me when I started, that seems like a difficult problem. How do we figure that out? And it turns out we're not going to do that problem. It's too hard for us, right? So we're going to do an easier problem. Let's think about rolling a six-sided die, and I really like the number 3. I want to know. I want to know how many times do I have to roll this dice before I will see a 3. Okay. So each time I roll the dice, I have a chance of getting a 3, a chance of a success. And so in my example, the chance of a success is just going to be 1/6, assuming I have a fair die. That's the chance of me seeing a 3 on any one turn. So what is the chance that I would see my 3 on my very first turn? Yeah. 1/6. I'm just going to call it P, okay? What is the chance that I wouldn't get it until my second turn, that I would get it exactly on my second turn? Right? And again, sorry if I'm banging you over the head with this, the way to think about this is really it's the chance that I don't get it on the first turn, and I get it, right? Magic word, independent event. We can use the and rule, and that I do get it on the second turn. So I'll write that as Q times P, where again, Q just is equal to 1 minus P. Okay. What's the chance that I'll get it on my third turn? And what's the chance that I would get it on turn T? Q to the what? T minus 1 times P. Awesome. You've just figured out the probability distribution for one of the classic probability distributions called the geometric distribution. Okay? So I've written that here. This is the geometric probability distribution for a geometric distribution. And it has mean of 1/P, which you probably sort of knew intuitively. If I said, what's the average waiting time for me to get my first 3, probably many of you would have just intuitively said, I think you'll have to wait 6 turns, right? Which is 1/1/6. It's 6. So your intuition in that case turns out to be correct. The mean of a geometric distribution is just 1 over the probability of success on any one turn. And it also has this variance, okay? Yeah. Okay. That's exactly our problem, right? We are asking, what's the chance that 2 alleles coalesce in 1 generation back? We're thinking, let's think about our ideal population. Well, now the chance of success is what? 1 over 2n, right? 1 over 2n. What's the chance that it would take two generations? Well, you would have to not coalesce in the first one, so 1 minus p, and then you do in the next generation, right? This is the same exercise as rolling the dice. So everything's exactly the same. We don't need to re-derive it. It's just that geometric distribution. And so then the average time to coalesce will just be 1 over p, which in this case is now 2n generations. Okay. I want to point out, though, well, okay. I also wrote down the variance. Remember the variance. So the variance is of this geometric distribution is 1 over p squared. In our case, if n is large, then this thing in the numerator is approximately 1, right? So in our case, this is going to be approximately 1 over 2n squared, which is 4n squared. I'm just pointing out there that the mean is 2n, but the variance is 4n squared. So there can be large variance in what these coalescence times are. Okay. We can use this to get the full distribution of coalescence times. Remember, the mean and the variance are just kind of summary statistics about that distribution, but they're useful ones. One thing I'll mention, so we're doing this in discrete time, right? We're thinking about discrete generations. The sort of more formal coalescence, the Kingman coalescence, is done in continuous time, which works quite well. You know, the time scale at which coalescences are occurring, right? The average time is 2n generations. So any a single generation kind of represents like an instant in time almost. So instead of using the geometric distribution, we often use the continuous time, essentially the equivalent of that, the exponential distribution, which has the form I've written here, where c is the rate of coalescence on the appropriate time scale. And I won't use it here because I think it's easier for students to not think about it that way, although in the Kingman coalescence, the time scale that you work on is not generations, it's 2n generations. That sort of 2n generations represents one unit of time on the coalescent time scale. But that's just a rescaling of time, okay? And if you work on that time scale, then the rate of coalescence works out to be 1, rather than thinking about 1 over 2n. I'll switch back and forth a bit between the geometric, using this discrete. I'll talk about things in terms of discrete time, but I'll often use this exponential distribution. Hopefully you won't be bothered by that. Okay, so where was I here? Okay, all right. So let's think for a moment about this chalkboard's so big that when I leave the eraser on one side, it's a long way back to go get it. So let's think about two samples. And let's think about the number of differences that would be between those two samples. So let's imagine these two samples coalesced T generations in the past. And let's imagine that mutation occurs at rate mu per generation. What's the expected amount of difference between these two samples? Pardon me? Mu t. Well, how did you get, mu t is close. How did you get that answer? Yeah, so, but that's really how many mutations that have occurred here, right? How many will have occurred there? Same, right? So so the total distance between from here to here is actually 2 mu t. I made an assumption to do that. What was the assumption? Yeah, that's one way of saying it, but sort of more, that's one way of justifying the assumption. The assumption is that all these mutations are unique, right? Because if I got the same mutation occurring here and here, then those were the only two mutations that occurred. These sequences would actually be identical, right? So this assumes all the mutations are unique. Or similarly, if I had a mutation occur at this time point, and then that same site mutated again, I would still only see one difference from, or possibly no difference if it was a back mutation. So it assumes every mutation is unique, which in actuality, if 2 mu t is not very large, then we would expect that would be true. Okay, so that was the expected number of mutations if the coalescence time was t. But now let's think about, on average, if I sample 2 alleles, how different will they be? Well, the thing we need to know is, what's the average time to coalescence? But we know that now, right? So if we plug in the average time to coalescence, so we instead call this the average time to coalescence, we multiply this by a factor of 2n, and we get 4n mu. Sound familiar? Yeah, that came up last time too, right? We call that theta. Any of you who read any molecular population genetics papers, you will have seen theta appear. You will have seen this 4n mu appear many times before. I hope now you're starting to get a context so that doesn't just fall from the sky, right? You guys hopefully now appreciate where these things come from. Okay. Okay, so we thought about 2 alleles coalescing. Let's think about if we start with 3 samples, the time until the first coalescence, right? So essentially, the time to go from 3 alleles back in time until we have 1 coalescence, leaving us with 2 alleles. Okay. It's really the same. It's really the same thing that we've done before, right? We're just waiting for a success. Now a success is defined as having a coalescence event. We don't care if it's sample 1 with sample 2, sample 1 with sample 3, or sample 2 with sample 3, right? We just want 1 coalescence event. So we have 3 samples. Any 2 of them can coalesce. So there's 3 choose 2 ways for possible coalescent ways to pick alleles to coalesce, and 3 choose 2 just works out to being 3, right? 1 with 2, 1 with 3, 2 with 3. So there's 3 possible coalescences that could occur. Each one of those occurs with chance 1 over 2n. So each one of those occurs with chance 1 over 2n. So the total chance of any one of those happening is 3 over 2n. Okay. So we would just repeat this whole exercise. This is the probability of a coalescence occurring. So we could just use the geometric distribution or the exponential distribution if we want to think in continuous time. And so on average, we would have to weight the 1 over this time. So that would be 2n over 3. That would be the average time, the average waiting time to go from 3 alleles down to 2 alleles. That make sense? Well, we can instead of thinking about, and then after that time, now we're back into the problem we did before, right? We're left with 2 alleles. That would follow a distribution with, I'd say, a geometric distribution where the probability of success is now just back to 1 over 2n, what we did before. Okay? We can generalize this a bit more and think about, instead of having 3 alleles, having k alleles, and the time it takes to go from k alleles to get the first coalescence, taking us down to k minus 1 alleles. And all I do is change this to k, which will no longer, in that case, be equal to this. But we do everything exactly the same, okay? And so then the No, that's just the time that will just give us the distribution of times to go from k down to k minus 1. And then we repeat the thing and repeat the thing and repeat the thing till we're down to 1. Okay? But we can say what's the expected waiting time to go from k to k minus 1, and it would be 2n over k choose 2. If you're not familiar with this k choose 2, this binomial coefficient, again, it's defined in the first set of notes. But for really the more important thing is just conceptually what it is, right? It's the number of possible ways to choose 2 things out of a set of k. Okay. So let's think about, so this is the expected, what I'll call TK, the expected time to go from k to k minus 1 alleles. Well, let's think about all the alleles in the population. So imagine our sample, k, is 2n. We sample all the alleles, and we want to know what's the total time for all these things to coalesce to a common ancestor. So in that case, the expected time to coalesce for all of them, the total to go from k down to a single allele is just going to be the sum of the average times to go from starting from k equals 2 to k equals 2n. Although we think of it really the other way, of going from 2n alleles down to 2n minus 1, 2n minus 2, all the way down to to k equals 2. And then remember this tk represents the time going from 2 down to the single allele, the last one. Right? Okay, well, we can just plug all this in. forgot to add one simplification. This k choose 2 is just equal to k times k minus 1 over 2. So this thing becomes 4n over k times k minus 1. Okay, so I'm just going to take that, plug it way over here. So we have this, we sum up this series. I'm not going to go through the details of how you sum this series, but this works out to being 4n times 1 minus 1 over 2n, which if n is large is approximately 4n. That's the time, the expected time for all the alleles in the population to coalesce. So I want to make 2 points about that. Well, I should both help with this. So the first point is that's the time for all the alleles to coalesce. Yeah, expected time. Remember, the expected time for just a randomly chosen 2 to coalesce was 2n. So having all those additional alleles only just doubles the time. And one way to think about that is illustrated by this figure that most of the time in a typical coalescence genealogy will be in the time for the last 2 alleles to coalesce. It's another way to think about it. If I sample any 2 alleles at random, a bunch of the time I'm going to get 2 alleles that are kind of on the same side of this genealogy, like in this half, and they'll have kind of short coalescence times. And then the other fraction of the time, I'll sample one from over here and one from over there, and I get this deep coalescence time. Okay. The other point, which is a bit more of the technical point, technically, I can't really do this summation, I can't really use this when k gets very large, because remember we made this assumption that having multiple coalescence events occurring at the same time isn't allowed. That's very unlikely. Well, it becomes extremely likely when you have all 2n alleles. But it turns out that doesn't really matter because all of those, there's a whole pile of coalescence that occur right in the beginning, and those add a trivial amount of sort of noise to this whole thing. And really, the bulk of the time comes after you get down to a sort of a much smaller subset of remaining alleles. So this approximation works quite well. So what people always say is k needs to be very small relative to n, right? So which is typically true, right? That the number of samples we get is much smaller than the number of organisms that are out there, right? Although now that sequencing is becoming cheaper and cheaper, that's not necessarily the case, in which case you need to worry about it a bit. But my point was, again, remember, a lot of that doesn't matter because basically you're not getting things quite right in this first, say, 100 generations, but you're working on a time scale that might be 10,000 or 100,000 generations. So you know, it's like I got Bill Gates' income wrong because I didn't account for the change in his pocket kind of thing, right? Like, you don't need to worry too much about that. And you know, that's one of the things that I want to emphasize about this coalescent way of thinking about things. We're going to, you know, we make various assumptions in doing this, and you know, some or many of them are not sort of strictly true, but I hope by sort of going through this exercise, you not only appreciate the sort of formal mathematical part of it, but that you also start building an intuition for how the process works. And that in doing so, you start being able to think on your own about what assumptions matter and are critical, and what others are just going to be sort of a trivial amount of error. Okay?
Can you elaborate a little bit more about the very striking result, right? The last half of the time,
Yeah.
the last two alleles sequenced. So how would that make you think about the biology differently? I mean, I'm just, you know, it's very striking application-wise.
Yeah.
Like it's conservation biology, I really like that example.
Yeah.
Do you have some other examples too?
Well, I mean, one sort of practical example is if you are trying to estimate the amount of genetic diversity in a population, you don't really need that many samples to get a reasonably accurate estimate of the sort of the average amount of diversity in a species, because the diversity that you're getting, and this is kind of where we're going to go next, you know, that comes along these long branches, right? All of this stuff is little iddly-piddly stuff, right? If you're asking about sort of heterozygosity, you know, that comes from these long branches, and you only need to get you know, if you think about sampling from across the top of this tree, you don't need to sample that many times to make sure that you've represented all these long branches in your sample. Yeah.
In this framework, can one not look at very recent history, like very recent times?
Well, I mean, I don't want to sort of overstate. You know, certainly, if you want to estimate rare, you know, the number of, if you want to estimate rare variants and estimate their frequencies confidently, then you do want to get a large number of samples, because you know, things that are rare are typically things that have occurred, mutations that have occurred recently, right? And so to accurately estimate their frequency, you need to have quite dense sampling across the top of this tree. But if you're just trying to get an overall picture of heterozygosity, you don't necessarily need that, right? So it depends a little bit on what your question is. There's certainly some interesting questions that you get power to ask a different kind of question if you've done this dense sampling, because you're getting this reflection, a better reflection of what's happening in more recent time. Okay, so yeah, I want to talk about the expected number of segregating sites in a sample now. Okay. Oh, sorry, am I way past already? Oh yeah, there's a red flashing light. Okay, sorry. Yeah. We'll stop there and continue next time.